As was already made painfully obvious by the title slide, for those of you who regularly attend the Waterloo Algebraic Graph Theory seminar, there's a lot of overlap, but this is not the same set of slides or deck as the young people say. So anyways, let's get started. So basically the question is, when are tuples of subspaces morally the same? So I know not a lot of you deal with like optimal subspace configurations, but I mean, we spent an entire week, for example, with Crystal last week talking about graph isomorphisms. When you have like new combinatorial designs, you can ask. So there's a lot of questions of this flavor. You want to ask, when am I getting something with new parameters? And even if it's the same parameters, when are there some other traits that I can use to distinguish these two things, these two objects? And I will only be focusing on the former for this talk today. Okay, so let's make it even easier and let's just talk about vectors. And so for this, I'm going to want people to speak up here. So when are vectors morally the same? I'm going to show you two sets of vectors. Oh, no, I'm not. That's the next slide. So certainly we want them to have the same number of vectors and be in the same ambient space, just like if we want to say if two graphs are the same, they need to have the same, number of vertices. What about anything else? Okay, here are the two different sets of vectors. Are these the same? Why or why not would you say that these two sets of vectors are the same?
I'd say yes, is one rotation of the unit.
Right. So, I mean, you could very clearly say this is not a well-defined question. You could very clearly say they're not the same because they're literally not the same. One's green, one's blue. But for the purposes of like the kind of questions I care about, the fact that these are rotations of each other means that they're the same. Okay. What about this set of red vectors?
It's by the antisymmetric product, right? Is that what you're doing? If the vectors are the same, it's B sub 3.
Well, maybe the hint is in the title of what I'm asking. Isn't it great to ask a question where you don't define what the question is? But the hint is in the fact that I'm talking about subspaces. These three red vectors, they span the exact same set of three lines as the blue vectors. So if we're using these vectors to represent lines, then by that, these are the same if we're thinking about them as lines. And then we have this set of orange vectors, which you might, if you really want to, say they're the same because it's a set of three vectors in R2 that span all of R2. But for the purposes of this particular talk, we're going to ignore that, although the paper that most of this comes from like includes this as a special case, but then you need different tools. Okay, so why do we care? I like nice configurations of vectors, and also I really like scare quotes here. This is kind of my jam. And more generally, subspaces. We're going to start with vectors because vectors are easier to deal with. And I'd like to know if a nice construction is new. So as a mathematician, I want to know, is this new? Have I done something new? Have I just rediscovered something that's already well known? And also another thing that I'm not going to have too much time to get into is that I'd like to know if one configuration is nicer than another based on properties of the substructures. And sometimes these methods applied to sub-collections actually can tell us some differences between things. So depending on how much time I have at the end of the talk is depending on how much I'll go into these details. So now I want you to assume that this is an interesting question. Okay, so let's go back to these three sets of vectors, not the orange one, but the blue and the green and the red. So when I think of vectors, I think of them as columns of a short fat matrix. One of my collaborators even has a blog called Short Fat Matrices. This is like, these are our bread and butter. So if we think of this set of blue vectors as phi1, and then we just read them off as the columns of this matrix, and they're just pointing to the third roots of unity. If we do the same thing with phi2, well, that's the same thing as taking phi1 and multiplying it on the left by a rotation. I mean, here it's a rotation by 90 degrees, so it's particularly simple, but it's rotation. And these red vectors here, well, the red vectors are the result of flipping this vector that was going down to the left to make it up and to the right by multiplying it by -1. So that's the same as multiplying this phi1 on the right by a matrix that's diagonal, and all the diagonal entries are 1 except for the -1 corresponding to the vector that's being flipped. So now let me actually define what I mean by same. So given tuples of n vectors, I'm going to call them phi and psi, and I'm thinking of them again as being columns of matrices. In FD, and whenever I use F here, I mean the reals or the complexes, we would like to know if they span sets of lines that are equivalent under some action of the unitary. So unitary for complex and orthogonal for real. This is the same as asking if there exists two different matrices. So these are n vectors in d-dimensional space. So if there exists a d by d unitary acting on the left of that short fat matrix, and an n by n diagonal unitary acting on the right of that short fat matrix to transform one to the other. So diagonal unitary means diagonal plus minus one in the reals, and diagonal unimodular in the complexes, because if you take any unit vector and you multiply it by a unimodular, it's going to span the same line. So multiplying a vector by a unimodular doesn't change the line.
What relation does this have to asking about the set of vectors, two sets of vectors with the same inner products or absolute values of inner product?
So what we will see is when this happens, you will have the same absolute values of inner products, but it doesn't go the other way. So then the question is, if you have things that have the same set of absolute value inner products, what more extra information do you need to be able to tell whether or not this information holds? So it is only a one-way.
But if you didn't allow this delta matrix, then it's the same as having the same inner products.
So yeah, so if you don't allow this delta, then this is going to say that they have the exact same gram matrices.
If and only.
If and only if, yeah. Okay, so in this talk, I'm going to call this isomorphic interlinear isometry, ILI, because the paper it's associated with, we call it that because we use this as a bunch of different cases. In particular, when we're talking about real equiangular lines, property is called switching equivalence, and we're talking about complex lines. In some papers, it's called projective unitary equivalence. So it has a number of different names. So we could also add in something a little more complicated and add in a right multiplication by some permutation matrix. So when I had those drawings of vectors, I arbitrarily chose how to stack those up into a matrix, right? That I made a choice when I did that. And so one could ask, oh, am I making the right choices? Okay, so let's go back to these three sets of vectors and the corresponding short fat matrices that represent these vectors, and refresh our memory on something we saw last week in Gary's short course, or Seidel matrices. So we first take the gram matrices. So as was already pointed out, the blue and the green are just rotations of each other. So we look at the inner products and they're exactly the same. But here, this red, where we flipped something, that's going to change some of these inner products. So the Seidel matrix is we make every diagonal element 0, and then for the off diagonal elements, we read off the sign of the element. So here we have -1s all off the diagonal here, and here we have just the one pair of -1s, and everything else is 1. And we can use these as adjacency matrices for graphs by saying -1 means there is an edge and 1 means there's not. So let's look at that correspondence here. So in this case, all of the off diagonal entries are -1. So that means we are dealing with the complete graph, and it's on 3 vertices. So these both correspond to the same graph. Over here, we have only one pair that has vertices that has -1. So it's a graph with one edge on 3 vertices. So let me step away from graphs for a second and define equiangularity. So we have some collection of vectors, n vectors in d-dimensional space. We call them equiangular if there's some positive or non-negative alpha, such that the absolute value of any 2 distinct vectors from that list have inner product alpha and 1 otherwise, so they're unit vectors. So why do we have the absolute value? So let's say we took the vectors x here in red and y here in blue, and they're unit vectors. By basic pre-cal or whenever you learned it, the dot product of x and y is going to give you the cosine of that green phi. But although we're playing with vectors, because dealing with projective things is complicated, we really want to talk about the lines. So if we take the absolute value of the dot product of x and y, then what we're getting is the cosine of this orange theta, i.e. the cosine of the non-obtuse angle between the two lines. So this absolute value means you're really forcing things to be thought about on the line level. And so the fact is that each tuple of non-orthogonal equiangular real vectors corresponds uniquely to a finite simple graph via the Seidel adjacency matrix. So if one finite simple graph may be attained from another by flipping the adjacencies of a sequence of vertices, and this is not a local thing, I'm doing this globally, had some discussions of local switching, then they are switching equivalents. So here, as a very simple example, we take this vertex, and it was adjacent to two other vertices, and now we switch the adjacencies so it's no longer. And if we had a vertex that had some vector vertices as adjacent and some was non-adjacent, it would switch which were adjacent and not adjacent. And a fact is that the parity of the edges on all induced subgraphs of three vertices uniquely determines the switching equivalence class. You take any graph, and for each triple of vertices, you say, is there an odd or even number of edges on this induced subgraph? And that gives you an invariant that tells you what the switching equivalence class is. And if we think about what that means, so we have an edge anytime the inner product, and this corresponds to Seidel adjacency matrices of real equiangular lines, anytime the inner product of the vectors is negative. So what that tells us is that what we care about, because we care about the parity of the edges, that's the same thing as caring about the signs of the products of the inner products that are on those edges. So if we look at for phi j, phi k, and phi l, the chain of these inner products, and the order is not so important for the real, but it will be later. So phi j inner product phi k inner product phi l inner product phi j, then looking at all of those sets of inner products, if we have a set of real equiangular vectors, will tell us whether or not those two sets of vectors gives us the same lines, if we aren't taking into account permutations of the vectors.
Bill Martin is asking, in the complex case, do you still consider the Seidel matrix?
So the answer is I don't know people who do, but this inspiration will be leading us to what we can do with complex cases. In the complex case, in the real case, there's only two things that your inner product can be. If you have real lines, a plus alpha or a minus alpha, and in a complex case, there's infinitely many. So like you could do like a weighted graph where all the edges are weighted by the different phases, but yeah, I'm not sure what that would get you. Okay, so the general one-dimensional problem. So we're taking two short-fat matrices. And the question is, if there exists a diagonal unitary matrix of the size of the number of vectors that we can conjugate the grand matrix of one to get the grand matrix of the other, then we say these things are isomorphic up to linear isometry, or projectively unitary equivalent or switching equivalent, depending on what you want to call that. So I'll just make a quick comment that quote unquote permutations are hard. I mean, again, we've seen this entire thing on graph isomorphism. And what might not be too surprising is if you also then try to figure out things that are equivalent, allowing for a permutation of how you label the vectors, then that's going to be graph isomorphism hard. And that's like the last I'm going to say of it on this talk. So if we have a set of real equiangular lines, then an invariant to know whether or not these lines are the same is by checking all of these products of inner products. But what about when vectors are not equiangular or not in RD and or not in RD? So let's look at these two sets of vectors. These are two sets of 9 vectors in 3-dimensional space. Those of you interested in quantum information, these are both examples of seek problems. They're a maximal set of equiangular lines in complex space. They're projected to design. There's a lot of cool, fun things that they are. Now, if we look at the absolute values of the entries of the Gram matrix, so these are all 1/2 off the diagonal. All the inner products of distinct vectors is 1/2 in absolute value. And just like we had in Crystal's talk, we build these matrices and we look at their spectra and they're the same. So we even look at the Gram matrices of these two different sets of vectors, and they even have the same spectra. So the absolute value of the entries are the same and the spectra are the same. But these two are not relatable. They're not ILI, they're not switching equivalent, they're not projectively unitarily equivalent. And one of the ways that you could see this, I mean, before I get into like how we're actually going to do this, is the linear dependencies of the vectors are different. So this set of 9 vectors up here, there are 12 different sets of 3 vectors that are linearly dependent. As this set here has only 3 sets of vectors that are linearly dependent. 3 sets of 3 vectors that are linearly dependent. So the linear dependencies cannot change if all we're doing is flipping the vectors by conjugating, or possibly multiplying by unimodular. So we need something more than just looking at these Gram matrices. Okay, so let's think about what it means vector-wise if we have these things that are equivalent. So if we have 2 sets of vectors that are equivalent, then what do we know? Well, it means that there is a single unitary. There's a single unitary that you can multiply each of the vectors on by the left, and then a sequence of unimodulars that you can multiply each vector. Well, I'm writing it on the right because we're thinking this coming from a right matrix multiplication, but it's a scalar multiplication that gets you from each of the phi j's to each of the phi j's. So if we look at these triple products that were helpful for us when we had real equiangular lines, let's just plug in. If we have that formula relating the phi j's and the psi j's, let's see what happens. So we write out that triple product, and now we replace each psi j with the unitary times a phi j times whatever that unimodular eta j is. Well, the unitaries go away. That's why they're unitaries, right? And then we can pull out these unimodulars, and I'll say I'm being a physicist in that I am making this conjugate linear in the first, not the second. We pull out all those unimodular constants because they're just scalars, and then those things can all commute because they're just scalars, and we can cycle everything around, and we get all the pairs of eta j bar, eta k bar, so on and so forth. So we get the same set of triple products, meaning that testing these triple products is definitely necessary in order to figure out whether or not these two things are equivalent. And in fact, this for those 2 sets of 9 vectors that I mentioned before, that is already sufficient. So those 2 different sets of 9 vectors, if you check their triple products, they're different. Okay, so can we always just test the triple products? The answer is no. So let's look at 2 pretty simple sets of vectors. They're all in R4. They all have 2 zeros in them, and there's 1s everywhere else except for this one has a -1 in this corner. So the absolute values of the Gram matrices are equal. In particular, that means if we look at these double products of inner products, then those are all the same, because they're all either going to be a 2 or a 0 or a 1, depending on like which set you get. And in fact, the triple products are all the same, because if you take any 3 distinct vectors from here, 2 of them have to be orthogonal, so the entire thing is 0. But if we were to actually look at the spectra of the Gram matrices, we could see they aren't the same. So we would actually know that these aren't the same. But the point is that the problem that arose here was that we had some vectors that were orthogonal to each other. And so when we started taking these triple products, that kind of hid the lack of equality. Okay, so we're going to call phi nowhere orthogonal if no 2 vectors are orthogonal. And then we just take our Gram matrix, and we take the signs of the Gram matrix on the very first row, and we're going to make a diagonal matrix out of that, and then we're just going to conjugate our Gram matrix. Then this normalized Gram is an injective invariant for this equivalence whenever we have something nowhere orthogonal. So this isn't the same line of normalized Seidel matrices, normalized Hadamard. We saw normalized conference matrices yesterday in Jason's talk. So then the normalized version of the three different sets of vectors, the red and the blue and the green, would all have this gram matrix that has 1 and followed by 1/2 in the first row, and then 1 followed by 1/2 in the first column, and then 1/2 with minus 1/2 in the off diagonal. So all three would lead to the same normalized gram matrix. Okay, so it ends up what we're going to need for the general case of vectors is to define these so-called M vertex Bargman invariants, or M products. So when M is 3, these are triple products. So just as before, we can play that same game and show that if we have two things that are ILI, that are equivalent, then clearly all the M products have to be the same. And now let's do another little manipulation here. So let's just look at what it means. I'm going to do something, rewrite this M product, and this is going to be helpful in the future. So again, I'm doing conjugate linear in the first entry. So this inner product of phi j1 and phi j2 is just the same as phi j1 star times phi j2. And we continue that. This is a number, and a trace of a number is equal to itself. So I'm just going to throw a trace on there. And now that I have a trace, I'm going to use the fact that the trace is cyclically invariant, and I'm going to move this phi j1 from the end to the beginning. So now I have the trace of phi j1 star, phi j2 star, and so on. And if all these vectors were unit vectors to begin with, that is simply the trace of the product of the projections onto the subspaces that each of those vectors span. So these products are the same as traces of certain, one could say, words in the projections onto those subspaces. Ends up that when we have a set of vectors that's no orthogonal, then the up to 3 products form an injective invariant for this ILI. So when we're equiangular, we're already assuming that each vector is unit norm, and that the inner product of all the vectors squared, or an absolute value, is going to be equal. And so that kind of automatically gets us the 1 and the 2 products, so then all we have to test is 3. And for arbitrary phi, then testing all the products up to the number of vectors suffice. But obviously, if you have a large number of vectors, this number grows very, very quickly. And I'll make one more comment that the number of triple products that equal -8 is different in those 2 different sets of 9 vectors in 3-dimensional space. So that is actually something that tells us that even if we permuted the vectors, they still wouldn't be equivalent. So for example, if you have 2 graphs and the multi-sets of the degrees of each vertex are not equal, then you know they can't be isomorphic. So this is sometimes you can get lucky and show things up to permutation. Okay, so we're almost done here with the vectors. So let's again we have our short fat matrix phi with vectors phi j. Then we'll define the correlation network, which some people later defined as the frame graph, but originally it was correlation network, to be vertices corresponding to the vectors, and you draw an edge if they're not orthogonal. Then, if this graph is connected, then the triple products form an injective invariant. So before it was much stronger. Before the result I said is if it's nowhere orthogonal, which means that this correlation network would be the complete graph. And now it ends up we can actually weaken that to say we only need triple products if it's a connected graph. And the proof basically uses you make a spanning tree and then you slowly start building in the triangles one edge at a time. So what about subspaces? That was on the title slide, as well as the wrong date and seminar name. Okay, so we're going to generalize this by saying now we want n tuples of r-dimensional subspaces of FD. So we can think about on a couple of different levels. The first level is just like when we were thinking about lines, we were playing around with vectors because who wants to play with projective things? I mean, I guess some people, but that's not what I'm into. So let's fix orthonormal bases, AI and BI, for each of those different subspaces. Then these subspaces are isomorphic up to linear isometry when there exists, so we still have a d by d unitary, so a change of basis rotation, that we can multiply this super short fat matrix that has, we're just stacking up all the orthogonal bases for these subspaces. So we can multiply on the left by some unitary, and on the right by a block diagonal unitary with block size r by r. So here we're acting kind of separately on each of these little things. So we can act on the right by an r by r unitary on A1 and by an possibly different r by r unitary on A2 all the way down. So this is the higher dimensional variant of I can take a vector or its negative and get the same line, or I can take a vector and any complex conjugate scalar of it, any unimodular scalar of it and get the same line. So this is how that happens there. Okay, so we're going to define what we mean by nowhere orthogonal for subspaces. They're nowhere orthogonal if U intersect V complement, orthogonal complement, and U complement intersect V is equal to empty set. This in particular forces this kind of symmetric condition forces that they're actually the same dimension. So let's look at three different subspaces. One is this set of vectors that in R3 where the third coordinate is 0. One is the set of vectors in R3 where the second coordinate is 0, and one is the set of vectors in R3 that is the span of 1, 0, 0 and 1, 1, 1. Then U and V are not nowhere orthogonal because, for example, the vector 0, 0, 1 is orthogonal to everything in U, but it also lies in V. But U and W are nowhere orthogonal. So we can think of these as like, we're thinking about these as planes like they are here, then they're planes that are kind of closer together and they're not orthogonal. Okay, so I skipped to, there we go. If we have an n-tupled nowhere orthogonal two-dimensional subspaces of FD, RD, sorry, that's a lie, then there exists an explicit algorithm to construct an injective invariant from the gram of the set of these ortho bases that's similar in spirit to the gram matrices with all positive first row and first column. Many, but unfortunately not most of the subspace configurations that I care about and Matt cares about, and maybe some other people in this room care about, satisfy this, but unfortunately not all of them. Okay, so Matt's going to be speaking after me, and I took a peek at his slides because he was way more prepared than I was, and his slides were already up. So I decided to take an example. We were talking about, take an example from the thing that you're about to see. And I got the MATLAB code for him, and then I computed this injective invariant for this set of 5 subspaces of 2 dimensions that he is going to be giving you this cool combinatorial construction of. And so we see it's like identities down the diagonal and scaled identities in the first row and first column. So you might just say, this seems trivial. Can't you just conjugate by a block diagonal matrix that like turns all of these in identity matrices? But it ends up there's some subtlety going on. In fact, we even have to take care and there's different cases for whether, so for this case, all of these like blocks have a certain spectrum, and we have to take a special case to prove that this is an injective invariant for these types of subspaces versus others. So it's maybe a little less obvious than one would think once you prove that this is actually an invariant. And without getting too much into things, but we use some H-star algebra representations and quiver representations to sort of create these explicit algorithms to construct words of projections that we can then take traces of in order to find if whether or not 2 sets of subspaces are the same, in quotes. And this doesn't need the nowhere orthogonality. This doesn't need any restriction on the dimensionality. So this is just something that is just free. And it generalizes these M products of vectors. But the key idea is these algorithms you have to do in polynomial number of steps. So it's not like you're getting this combinatorial number of words that you have to like check the traces of. So for example, using the code that we wrote with the paper, we take the subspaces that one can take from this talk that Matt's going to give, then run the algorithm to find the required list of words, then they're all the words in the corresponding subspace projections up to length 3, which is what we had with equiangular lines. And that set of subspaces are, in some sense, like equiangular subspaces. So it's kind of what you would hope would come out. And it is what indeed comes out. And the subspace test to be equivalent. So basically, I factored one gram matrix, and then I factored the other gram matrix, and then I randomly spun it up, and then I compared the subspaces. Okay, so why should we care? We got like, I don't know, about 10 minutes maybe. Okay, so let me explain to you what a couple of different words that you might hear us saying. So we're going to start with a collection of projections, and in this case I mean orthogonal, so idempotent self-adjoint projections onto subspaces of FD. If there's some constant A such that for all x in our vector space, we can reconstruct x by projecting it down with these PIs, summing that up, and then multiplying by 1 over A, then the PIs or their subspace images, there's a lot of kind of duality in whether or not you're talking about the projection or the images, form what's called, well, in like my parlance, tight fusion frames. If you talk to someone with quantum information, it's a positive operator value measured, which we saw on day 1 of this week. Now, if we then further, sorry, not further, if we go back, so now we aren't necessarily assuming it's a POVM. We're going back to just having a collection of orthogonal projections. So we have some collection of orthogonal projections, and they all are the same rank. They all rank R. So we didn't need that for this definition, but we do for this. So all rank R. And if we take the trace of the product of 2 projections for I not equal to J, and we maximize that, then if this minimizes that amount for a fixed dimension R, number of subspaces N, that should also be a D for the ambient dimension and field, then they form what is known as a Grassmannian fusion frame or a Grassmannian code, and they end up being optimally robust to noise and erasure. So these, like all these citations right here, are like the optimality sort of results. There's lots of different papers you could talk about this definition, but I just put the optimality results there. So they're optimal in some sense. It ends up that if you have something that is an equal rank type fusion frame, or AKA a positive operator value measure, and the trace of the products of any projections is constant, then it's automatically a Grassmannian fusion frame. So it automatically has this optimality condition. And the 2 different names that you could see in frame theory or quantum information would be an equiquartal fusion frame or a symmetric POVM. And when each of the ranks of these projections is 1, they form what's known as equiangular type frame. And when it's very highly structured, equiquartal fusion frames are called equiisoclinic, and Matt will be talking about that. Okay, so what are some examples? All of those sets of vectors we saw at the beginning, the blue and the green and the red, those are all equiangular type frames, which means they're also all the other things that were on the previous 2 slides. We center a few of the platonic solids, but not all, at the origin, and then we shoot vectors at each of the pairs of antipodal vertices, or we could think even easier, we just put lines through each of the antipodal vertices. Then that forms an equiangular type frame. Both of those sets of 9 vectors in 3-dimensional space formed an equiangular type frame. And the existence of such D squared vectors in D-dimensional complex space that are equiangular type frames is a big open problem in quantum information called Zauner's conjecture. And there, these are called symmetric informationally complete positive operator valued measures, or seek problems, or even shorter seeks. And in frame literature, they would be called, Gabor ETFs. Some more examples tying back to Gary's talk. Whenever we have real equiangular lines that have Seidel adjacencies that have 2 distinct eigenvalues, those are real equiangular type frames. In fact, it's one-to-one correspondence. I can't remember when we heard this, but at some point since I arrived here, someone had talked about is built mutually unbiased spaces. So when you have a maximal set of mutually unbiased spaces, these aren't equiangular type frames because some vectors have inner product 0 and some have inner product 1 over the square root of d, but they are actually these Grassmannian frames. So when you have that many vectors, they are the most spread apart of any set of vectors that are that numerous. SRGs, which we've seen a ton of different times here, with certain parameter classes yield real ETS. In fact, the ones with a certain parameter classes, this isn't a one-to-one correspondence. And finally, these are all one-dimensional subspaces, but Matt is going to be talking about higher dimensional subspaces, in particular, this example of 5 subspaces of dimension 2 in 5-dimensional space. And that is an example of these really highly structured things called equiisoclinic, which are actually in turn equichordal. Okay, so another thing to mention, some shameless self-promotion, there's this game of Sloan's that trying to gamify the search for optimal packings of complex projective and complex projective space, which I actually have received some new things. I need to update the website, but got Henry Cohn sent in a few new things that have beat these things. But the idea is we have these values, try to beat them, try to find vectors that are more spread out. And the hope is we'll eventually get some things that are numerically so good that we can actually kind of figure out what an exact representation of the vectors are. And then we can actually prove that these things are optimal. And I'm going to end with just a little side note. And I didn't make too many slides on this, so which is good because there's not a lot of time left. So we go back to that set of one of those sets of 9 vectors in 3-dimensional space. And I said that there are 12 different sets of vectors in here, sets of 3 vectors that are linearly dependent. And we can look at the first 3 and you just look at it, and clearly those span a subspace of dimension 2 because they all have 0 for their middle coordinate. Same thing for the second set of 3, they clearly span a subspace of dimension 2 and therefore are linearly dependent. And the last set of 3, it ends up there's 9 further sets of size 3 that are linearly dependent. Actually, they correspond precisely to the Hesse configuration or the affine geometry over the plane of over the field of 3 elements. But it ends up these triple products can reveal hidden properties of these vector subcollections. So this is one in an infinite class of types of equiangular type frames that have certain hidden combinatorics in their linear dependencies. If you're into matroids, it's saying that like the slice of all the dependent sets, the circuits that are of girth size actually form a balanced and complete block design. And this is something that we can understand better using these types of triple products. And understanding when these dependencies occur has implications for compressed sensing, confirmation. So there's a series of talks by like Marcus Appleby and Ingemar Bengtsson, others where they are leveraging things about sub-collections of seeks and trying to use that to build up further chains. Grassmannian spectrohedron packing. So when you have these special sub-collections, they can sometimes then be leveraged to make better subspace packings for higher dimensions than 1, and extremal combinatorics. So it was mentioned before, Neil Gillespie's conjecture on the existence of maximal real equiangular lines, and it leverages some assumptions about subcollections of the vectors satisfying certain things. So these variants can be used to discover if one has discovered a new construction and to better understand the substructures of optimal configurations. It would be really nice to remove the nowhere orthogonal and subspace dimension 2 requirements, this Graham matrix ILI invariant. So remember, we went from for the vector saying we have this result for no pairs of vectors are orthogonal, and then you're able to move that to, oh, we just need that the correlation network is a connected graph. And so it would be nice to be able to do the same thing with subspaces, but we have not yet been able to do that. Yeah, so thanks for your attention. The paper software are on my webpage. And shameless self-promotion, some of you already know, some of you have spoken in this already, but I co-organized a seminar called Codes and Expansion on the theory and applications of harmonic analysis, combinatorics, and algebra. And you can go to the website and sign up for the mailing list if you're interested in attending. Thank you.
Are some questions?
In isoclinic case, do you think that?
The isoclinic case, do you think that we can just always use words of length 3 in your terminology?
Yeah, I think that would be a nice thing to be able to prove. I would hope that's the case. It was basically, it was the isoclinic case that had to be a separate case when we were proving the gram matrix invariance. And the gram matrix invariance is almost equivalent to saying that triple products suffice. Like if you do the right math, if you can make a gram matrix invariant, it's like, oh, you could do triple products. And actually, we do have, we didn't put it in the paper, we do have this result for other dimensions, like not just dimension 2, but we couldn't get the equi-isoclinic case to work. It was only when it was explicitly not equi-isoclinic that we could do the gram matrix invariant. And we were like, well, whatever, let's not include that. But yeah, so that would be great, but we didn't figure out how to prove that.
Questions? Not, we can thank the speaker again.